Since this is the last part of this COVID-19 series, we're going to need you to have information from all the other two parts that we had posted, since the pen model will be really important in understanding some of the topics. For example, today's agenda consists of two main things, which are the exponential and logistic regression. And also, we're going to do a final hands-on with the TI so that you guys can check your model and also get to know if it's accurate. The term exponential is formally defined as becoming more and more rapid. And thus, we could infer that an exponential curve, which by the way looks like this, is a graph whose gradient or slope increases when we increase x. Hence, the equation of an exponential curve, which a lot of you are familiar with, is ax to the power b, where as an increase in x is caused, there is a higher multiplier or gradient between each pair of points. Now, let's talk about a textbook example of exponentials, which is known as virus spread. In the last video, we discussed the pen model, which, as we discussed, had three main factors: the probability of infection, the exposure to others, and the number of cases. I'm going to call them P, E, and N for simplicity from now on. If we take a community of people and then for the number of new cases, we multiply P, E, and N, we could say that the cases for the next day, in this case NC1, is equal to NC plus P into E into N, which is simplified into 1 plus P into E into NC. Now, if the number of new cases is proportional to the number of existing cases, it means that each day you're going to have to multiply it by some or the other constant. And this means that moving forward, d days is the same as multiplying by that constant d times. Here's the equation once we do that. Now, even in perfect situations for viruses, the constant 1 plus E into P will decrease because either most people are infected, so there's a loss in E, or people's immune systems have caught up, which causes a loss in P. Now, I too was pretty confused at this point, but after watching 3 Blue 1 Brown's video on logistics, I realized that the P in our equation would have to include some sort of factor to account for the people already infected. In this case, we would take something like 1 minus the proportion of people in the world who are already infected, which in this case, as you can see, is 1 minus the number of infected by the population size. Now, let's pop this into our original PEN model, where instead of P, we put the constant that we just found. This equation, when plotted, looks like this. In mathematical terms, this curve is called a logistic curve. It looks almost indistinguishable to the exponential one we just saw earlier, except for that sharp decline that you'll notice on the top. More on that in a bit. But many mathematicians call this the more realistic curve, since even for a virus, it can't infect more than 7 billion people, or the total population. Hence, true exponentials almost never exist in the real world, since most of them surely but slowly reach a limit. Let's dive deeper into the semantics of this curve. First off, the gradient at each point, or the derivative for those of you who know calculus, increases till a certain point and then decreases after. This point is known as the inflection point. To find the inflection point, we need to know about the growth factor, which is measured by the total number of new cases today divided by the number of new cases yesterday. Now we can tell exactly where the growth factor is, since behind it there is a growth factor greater than 1. After it, there's a growth factor less than 1. And exactly at it, we have a growth factor of 1. To start off, like usual, we're going to first copy the data from our data set from day 29 to approximately day 147 and then paste it on our GDC. After that, we're going to name a variable, one for cases and one for time or day. This will help us make our time series model. The next thing that we're going to do is open a graphing tab. The graphing tab will allow us to visualize this by adding the time to the x-axis and the cases to the y-axis. And as you can see, the data points fit almost like a logistic curve. Thus, we can easily do regression of this by clicking menu for 6 and selecting logistic regression. Another thing that I like to do is add the same function to our spreadsheet tab. The advantage here is that you're able to see the parts of the equation A, B, C, and also get it plotted on the graph as F1 or F2, whatever you save it as when you're making the equation. You can do this by pressing menu for 1 followed by whatever regression you want. To check our model, we're going to use the term called residual. A residual is the vertical distance between a data point and the regression line. Each data point has one residual, and the residual can also be expressed with an equation. In this case, we can do two things with the residuals. We can do a residual plot, as you can see, and we can have the mean residual of all points, which shows up in our statistics page.